Okay, this is lesson 15 on related rates. But let me start by asking if there are any questions about implicit differentiation or logarithmic differentiation.
Can you do question number 19?
On which section?
3.5.
Sorry?
Lesson,
Section?
implicit differentiation.
Oh, 3.5. Okay, and number 19?
Yeah.
So this is the equation defined implicitly by the curve x squared minus 3 times the log of y plus y squared equals 10. Right? Is that the problem?
No, I'll read it.
So you have a different book.
Yeah. The question is 4x cubed plus natural log of y x squared plus 2y equals 2x.
Okay. So in the 5th edition, that's number 21, 4x cubed
Plus
the log of y squared plus 2y equals 2x. Right, so I'll do both of them. Let me start with the one you asked about. So this is the same as 4x cubed. It just simplifies it slightly. The log of y squared is the same as 2 times the log of y plus 2y equals 2x. And I want to differentiate both sides with respect to x. Of course, the derivative of 2x is just 2. That's easy. When I differentiate this with respect to x, the derivative of 4x cubed is 4 times 3x squared. When I differentiate log y with respect to x, this is the derivative of log y with respect to y times dy dx. And then this is plus 2 times dy dx. So this is 12x squared. Log y differentiated with respect to y is just 1 over y dy dx plus 2 dy dx. So this is the same as 12x squared plus, I can factor a dy dx out of these two terms. I get 2 over y plus 2. So this is all equal to 2. So 2 over y plus 2 dy dx is 2 minus 12x squared. So just divide by this. Dy dx is 2 minus 12x squared divided by x. This is the same as 2 plus y over y. So when I divide by it, it's y over 2 plus y. So there's a little bit of algebra here. Let me get through it again. So 4x cubed plus log of y squared, which is 2 log y plus 2y equal 2x. If you differentiate with respect to x on the right-hand side, of course, you just get 2. On the left-hand side, this is 12x squared. You differentiate this with respect to x, you get 2 over y dy dx plus 2 dy dx. So that's 12x squared plus 2 over y plus 2 times dy dx equals 2. And then you solve this equation for dy dx. And that's what you get. Are there any questions about that? Well, since I wrote it down, let me also solve this problem. When I differentiate this with respect to x, I get 2x plus 3 Derivative of log y with respect to x is 1 over y dy dx. Derivative of y squared with respect to x is 2y.
Professor, can you move the paper a little bit? Thank you.
It's 2y dy dx. The derivative of 10 is 0. So I get 3 over y plus 2y times dy dx. Bring this over to the other side is minus 2x. So this is the same as 3 plus 2y squared over y dy dx equals negative 2. So dy dx equals, just multiply by the reciprocal of this, I get minus 2y over 3 plus 2y squared.
Won't it be negative 2x and not negative 2?
2x. Oh, yeah, when I brought it over, should have been 2x. Thank you. I just took this 2x and moved it to the other side of the equation.
I also have another question. It says negative 3 ln y, right? Log of y. But then why did it become positive 3?
Oh, because I was in a rush. Thank you. Other questions about this?
Yeah, I'm sorry. So at the end, the x disappeared. How did it like disappear? Or is
Sorry,
that
where?
like at the end where it says negative 3 plus 2y? Yeah. Oh, okay.
Yeah. Okay. Well, we can use implicit differentiation to find the derivatives of inverse functions. So what is an inverse function? Suppose you have some function y equals f of x, let's say for x between a and b, and suppose f of x is either strictly increasing or strictly decreasing. That means when you graph it from a to b, if it's increasing, it's just going up, maybe from c to d. So f of a is equal to c, and f of b is equal to d, and this function is strictly increasing in this interval. So what this means is for every x, of course, there's some y is equal to f of x, and which is between c and d. But it also means if you take any y between c and d, there's exactly one x between a and b for which f of x is equal to y. So for all y such that y is between c and d, there is a unique x such that x is between a and b, and f of x is equal to y. So for every y, there's some unique x. So this defines the inverse function. Let's say for every the inverse function from the interval from c to d to the interval from a to b. So for every y, f inverse of y is some number x. So this is defined by, so for every y, you get an x, and the x is the x such that f of x is equal to y. So we start with the function f, which maps this interval into this interval, but it does it in a way which is sort of one-to-one. This is for every x, there's exactly one y, and for every y, it comes from exactly one x. So if I give you this y and I say find the x, that's a function, and that's called the inverse function. Okay. So for example, simple examples, suppose y is equal to x squared for x between 0 and 2. So that function looks like this. It's the parabola. So for every x, there's a y. Y is equal to x squared. So f of x is equal to x squared. And what is the inverse? F inverse of y is the square root of y. The inverse of, if you have y equal x squared, that's the same as x equals the square root of y. So the function y goes to the square root of y, that's the inverse function. So this is an important concept which you've seen before, even if you may not have used these words. What are some other examples that you know and love? Well, if you take the function y equals f of x equals e to the x, that's the exponential function. So this is for all x from minus infinity to plus infinity. You have the exponential function. And y equal e to the x, this is y is between 0 and infinity. The exponential function is positive. This is strictly increasing. What is the inverse? Well, if y equals e to the x, that means x is the natural logarithm of y. That's the inverse function. So f inverse of y equal log y, or we can write f inverse of x equal log x, if you prefer using x as your variable, is the inverse of the exponential function e to the x. And a property that the inverse function always satisfies is the following. So this is the sort of the fundamental property of an inverse function. If you take x, apply the function f to that, you get f of x. Apply f inverse of that, that gives you x. And similarly, if you start with x, then you compute f inverse of x, and then f of that, that's also equal to x. And this is exactly how we worked out the derivative of the logarithm. So suppose I have f of x equals the log of x. Suppose I let g of x be f inverse of x. That's e to the x. And what we know is that f composed with g of x is equal to x. A function composed with its inverse is the identity. So if we differentiate with respect to x, this is what we get. Now, the derivative of x with respect to x is 1. And by the chain rule, this is f prime of g of x, g prime of x. So this is f prime of e to the x, g prime of x. Well, g of x is e to the x, the derivative is e to the x. So this implies that f prime of e to the x is 1 over e to the x, or if I let e to the x equal t, f prime of t is 1 over t. F prime is f is the log, so this is the derivative of the log of t. I could also have composed the functions in the opposite order, and we get something slightly easier perhaps to look at. So if we have f of x equals the log of x, g of x equal e to the x, suppose I look at g composed with f. G composed with f of x, this is g of f of x, this is g of the log of x, that means e to the log x, which we know is equal to x. Because the log is the inverse.
Wait, can you go to the back page for a second, please?
Excuse me?
Can you go to the last page for a second, please?
Sure. So I'm going to repeat it right now. So if I take the derivative, so I use the chain rule. If I take the derivative of g composed with f of x, that's g prime of f of x, f prime of x. G of x is e to the x. The derivative of e to the x is e to the x. So this is g of f of x times f prime of x. This is g of f of x. This means e to the log x times f prime of x. This is equal to e to the log x, x, f prime of x. But g composed with f of x is x. This is the derivative with respect to x of x, which is 1. So 1 equals xf prime of x, which means f prime of x is 1 over x. What is f? It's the logarithm. This is the derivative of the log of x. So this is another way to work out that the derivative of log x is 1 over x. What about the inverse trig functions? So if we have y equals the sine of x, what does that look like? Looks like that. 0, pi, 2 pi, minus pi, minus 2 pi, minus pi over 2, plus pi over 2. The sign goes from -1 to 1, but it oscillates. It's not 1 to 1. So sine x is not strictly increasing or decreasing. So not strictly increasing or decreasing as you go from minus infinity to plus infinity. So you can't have an inverse function for the whole line. But if you look at the sign just from minus pi over 2 to plus pi over 2, that's what the graph looks like. So y equals sine x is strictly increasing for x between minus pi over 2 and plus pi over 2. So we can find an inverse function there.
Okay, I have another question. Where did the 1 come from? Where it says 1 is equal to x?
So this g composed with f of x
I
is
can't
equal
see.
to x. So the derivative of g composed with f is the same as the derivative of x, which is 1. So 1 is equal to this. Right? The derivative of g composed with f is the same as the derivative of x, which is equal to 1. So this is 1 equal to x f prime of x. That's where the 1 comes from. G composed with f, that's e to the log x, that's x. So when you differentiate with respect to x, on this side, you get 1. And on this side, you get x f prime of x. All right. So let's look again at the graph of the sine just from minus pi over 2 to plus pi over 2. It looks like this. So this is y equals sine of x. Now the inverse function is going to go from -1 to 1. It answers the question, given a y between -1 to 1, what's the value of x such that the sine of x is equal to that y? And when y is -1, the x is minus pi over 2, or if you just interchange x and y, this is minus pi over 2. When the sine of x is 0, x is equal to 0. When you have the sine of pi over 2 is 1, so the inverse function of 1 is pi over 2. And this is the graph of y equals the inverse sine of x, which we also write as arcsine of x. There are two different notations that we use. This is the graph of the inverse sine of x. So suppose we let f of x be the sine of x, and we let g of x be the arcsine or inverse sine of x. So what we know is that f composed with g of x, this means the sine of the arcsine of x is equal to x. So the derivative with respect to x is the same as the derivative of x of the sine of arcsine of x. Or it's easier to write derivative of s composed with g of x. The derivative of x with respect to x is 1. By the chain rule, the derivative of this composite function, this is f prime of g of x, g prime of x. If y is equal to f of x, the derivative of the sine is the cosine. So this is the cosine, f prime, of g of x, the cosine of arcsine of x, times the derivative with respect to x of the arcsine of x. Right? This is what we want to find. This says that the derivative of the arcsine of x is 1 over the cosine of the arcsine of x. That looks a little bit complicated, and we can use some elementary geometry to find a nicer expression for this. So I want to find the cosine of the arcsine of x. So this means find the angle. So arcsine of x is the angle whose sine is equal to x. So suppose we let theta be the arcsine of x. That means that the sine of x, means the sine of theta is equal to x. So if we have this angle theta, the sine, it's this over, it's x. This is x. And if this is a right triangle, this is 1 and this is x, by the Pythagorean theorem, this is square root of 1 minus x squared, because this squared plus this squared equals 1. So cosine of theta is the square root of 1 minus x squared. And what we had shown on the previous page is the derivative of the arcsine of x is 1 over, what was it? The cosine of the arcsine. Theta is the arcsine, so this is the cosine of the arcsine of x is square root of 1 minus x squared. So that's what goes in this denominator, 1 over the square root of 1 minus x squared. So this is one more very important differentiation rule that you need to know. The derivative of the arcsine of x is 1 over the square root of 1 minus x squared for x strictly between minus 1 and plus 1. Okay. Let's work out one more inverse trig differentiation rule. So let's find the derivative with respect to x of the arctangent of x. So let's just start by drawing a picture so we can remember what the graph of the tangent and the arctangent look like. So tangent x is sine over cosine. It's not defined where the cosine is 0, which is at minus pi over 2 and plus pi over 2. If you look at the graph of y equals the tangent of x, looks like this. We have vertical asymptotes at pi over 2 and minus pi over 2. But this is strictly increasing between minus pi over 2 and pi over 2. And it goes from minus infinity to plus infinity. So the arctangent is defined for all x from minus infinity to plus infinity. And it has horizontal asymptotes at pi over 2 and minus pi over 2. And the graph looks like this. This is the graph of the arctangent. It's defined for all x, and it has these horizontal asymptotes at minus pi over 2 and plus pi over 2, and the graph looks like that. So suppose we let f of x be the tangent of x, and g of x be the arctangent of x. So what we know is that f composed with g of x, this is the tangent of the arctangent of x. This means this is the angle whose tangent is x, so the tangent of that angle is x. So let's differentiate. The derivative with respect to x of x is the same as the derivative with respect to x of f composed with g of x. The derivative of x is 1. By the chain rule, this is f prime of g of x, g prime of x. This is what we want to find. We want to find g prime of x. We know f prime of x. F is the tangent. We know that f prime of x is secant squared x. The derivative of the tangent is the secant squared. So we get 1 is equal to f prime, that's secant squared x, which is the same as 1 over cosine squared x. So this is 1 over cosine squared of the arctangent of x. Actually, I think there's a better way to do this. So this is true, but I'm going to do it slightly differently. Because, so we know that f prime of x is secant squared x, and we have a relationship between secant squared and tangent squared, right? Remember that sine squared x plus cosine squared x equals 1. If you divide by cosine squared x, you get tangent squared x, because sine over cosine is tangent. Cosine over cosine is 1. 1 over cosine is secant squared x. So f prime of x, which is secant squared, is the same as 1 plus the tangent squared of x. So let me write this down again, because I have to go to a new page. We have the derivative of the tangent of x is secant squared x, which is 1 plus tangent squared x. And if f of x equals tangent x, g of x equals arctangent of x, f composed with g of x, which is the tangent of the arctangent of x, is
Professor,
equal
can
to
you move
x.
the paper?
Excuse me?
The paper, yeah.
So this is just the rule, the derivative of the tangent is the secant squared, which is the same as 1 plus tangent squared. So when we differentiate, the derivative of x with respect to x is 1. That's the derivative of this composite function. This is f prime of g of x, g prime of x. This is the derivative of the tangent. The derivative of the tangent is 1 plus tangent squared. So this is 1 plus tangent squared of g of x times g prime of x. What is the tangent of g of x? This is the tangent of the arctangent of x, that's x. So this is equal to 1 plus tangent of g of x all squared, 1 plus x squared, g prime of x. So this means that g prime of x is 1 over 1 plus x squared. G prime is the arctangent. This is the derivative of the arctangent of x. And that's what we needed to find. So these are our two sort of fundamental differentiation formulas for inverse trig functions. These are things you must know. The derivative of arc sine x is 1 over the square root of 1 minus x squared. Derivative of arctangent of x is 1 over 1 plus x squared. So these are two fundamental facts. Any questions about this? I mean, this is just stuff you have to study and learn. It's not supposed to be hard, but it's also not supposed to be easy. It's just, it is what it is. Okay. So there will be a lot of homework problems involving these differentiation rules, and I'll go over homework problems on Monday. But now we start a new section, 3.7, on related rates. So these are applied problems using calculus, and they're interesting, but they take some thinking to get used to a little bit. So let me start the way the book does in section 3.7. And suppose you have a cone. And if you have a right circular cone, it has two parameters. It's the radius of the circle at the top of the cone. And there is also the height of the cone. And the formula for the volume of a cone, V is, if this were a cylinder and not a cone, the volume would be the cross-sectional area, which is the area of a circle of radius r, pi r squared, times the height. If this were a cylinder, this would be a volume. A cone is always 1/3 the volume of the cylinder. So this is a formula for the volume of a cone. And now you see it, so now you have to know it. And you can think of this cone as being filled with water, and then you put a hole at the bottom so water is flowing out. And you want to know what is the relationship between the amount of water left. So if the water flows out, the water is filling up cones of smaller and smaller height and radii. And you want to know how these are related. So volume is some function of time. Radius is some function of time. And the height is some function of time. And the relationship is the following: dv dt is the derivative of 1/3 pi r squared h. That's 1/3 pi times the derivative of r squared h. By the product rule, that's 1/3 pi, the derivative of r squared with respect to t times h, plus r squared times dh dt. And what's the derivative of r squared with respect to t? That's 2r dr dt times h plus r squared dh dt. So this gives a relationship between these three changing quantities. As the water drips out of the tank, and you just look at the cone of water that's left, the volume is decreasing, the radius is decreasing, the height is decreasing. And those three rates, those three derivatives, are related according to this equation. Okay. So example 1. So you have x and y are some functions of time, of t, and are related by the following equation. It's simply y equals x squared plus 3. So y is changing, x is changing, but there's a relationship between them. So here is a problem. Find dy dt when x is equal to 1 and dx dt equals 2 when x equals 1. So let me just see, let's see what this means. So we have y equals x squared plus 3. So if you differentiate with respect to time, with respect to t, you get this. So that says dy dt, the derivative of x squared with respect to t by the chain rule is this is 2x dx dt plus 3. So this relates dy dt and dx dt. When x equals 1, dx dt is 2. So this becomes 2 times 1, x equals 1, times dx dt plus 3 . Oops, I'm sorry. I made a stupid mistake. The derivative of 3 is 0. So dx dt, 2x dx dt is 2 times 1 times 2, which is 4. So that's the answer to the problem. Y equals x squared plus 3, but y and x are functions of t. When you differentiate with respect to t, you get dy dt is 2x dx dt. When x is 1 and dx dt is 2, you get 4. That's the answer to this related rate problem. Okay, any questions about this? We're actually going to spend today and a chunk of Monday on related rates because they're very important problems and they're hard. They're hard, it's certainly hard in the beginning. They take a little bit of time to get used to. Okay. Example 2. Ripples in a pond. So you have your pond and you drop in a pebble. And what happens is it creates waves moving out from where the pebble hit the calm pond. The waves are concentric circles. Circles with the same center. So a pebble, I'm just going to read example 2 from the book so you can follow it better at home. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So you drop in the pond, this ripple starts propagating outward. It's a concentric circle getting bigger and bigger and bigger. And we're given that the rate, dr dt, at which this outer ripple is moving is moving at a rate of 1 foot per second. So at any given time, the amount of water that's being disturbed is what is inside this circle. So when the radius r is equal to 4 feet, what is the rate at which the total area of disturbed water is increasing. So there's a simple relationship between the area of a circle and the radius. So we have this relation, A equals pi r squared. So the rate of change of the area is the rate of change of pi r squared. This is pi times the derivative with respect to t of r squared. That's pi times the derivative of r squared with respect to r dr dt. The derivative of r squared with respect to r is 2r, so you get 2 pi r tr dr dt. Well, dr dt is equal to 1, and we want to know the rate at which the area is changing when r equals 4. So at r equal 4 and dr dt is constantly equal to 1, this is 2 pi times 4 times 1, or 8 pi. So when the radius of the outer ripple is 4 feet, the rate of change of the area of the water inside this wave is 8 pi square feet per second. You know the dimension is feet squared because it's area. Okay. Any questions about this? All right. Then, next problem. This is example 3. So this is inflating a balloon. A balloon is a sphere. Sphere is determined by its radius. What's the volume of a sphere? V, the volume, is four-thirds pi r cubed. You expect it to be r cubed because dimensions of volume are in cubic feet or inches or meters, whatever is your measure. This is the formula for the volume of a sphere of radius r. So you have a pump puts in air. At what rate? Is in terms of a certain number of cubic feet per minute. So you're told that the volume is increasing at a rate of, in this particular problem, 4.5 cubic feet per minute. And as you pump in air, the balloon gets bigger. So the radius is increasing. So our problem is find the rate at which the radius is increasing at the time when the radius is equal to 2 feet. Now, you have to think about this a little bit. As you're pumping in air at a constant rate, when the balloon is tiny, when you put in 4.5 cubic feet of air, it increases the volume and the radius a lot. When the balloon is huge and you put in another 4.5 cubic feet of air, the radius increases, but only by a little bit. So dr dt isn't constant, dr dt is changing. It's actually, you would expect it to be a decreasing function, that it's getting smaller with time. Okay, well, so from V equals 4/3 pi r cubed, if we differentiate with respect to t, we get 4/3 pi derivative of r cubed dt. That's 4/3 pi derivative of r cubed with respect to r dr dt. That's equal to 4/3 pi. The derivative of r cubed with respect to r is 3r squared times dr dt. These 3's cancel. You get 4 pi r squared dr dt, and that equals dv dt, which we're told is 4.5 or 9/2. So we get that dr dt is 4 pi is 9/2 times 1 over 4 pi r squared. So that's 9 over 8 pi r squared. And what is this equal to when r is equal to 2? Dr dt is 9 over 8 pi times 2 squared. 2 squared is 4. 4 times 8 is 32. This is 9 over 32 pi. Feet per minute. Questions about this?
Where did the 9 come from?
Well, we're told that dv dt, the rate that the pump is pumping in air at a rate of 4.5 cubic feet per minute. 4.5 is just 9/2. I just preferred working with fractions. Right? 9/2. So the 9 comes from 9/2, which is 4.5. That's the information we were given about the efficiency of the pump.
Okay, thank you.
Example 4. This is speed of an airplane tracked by radar. So here on the ground is a radar tracking station. And a plane is flying in a straight line at a constant height in a path that takes it directly over the tracking station at a height of 6 miles. So the plane is flying in this direction. And we let S be the distance from the radar station to the plane. So we're given some information when S equals 10 miles. See what the radar measures, it sees where the plane is and how fast this length dsdt is changing. When S equals 10 miles, dsdt, we're told, is decreasing at a rate of minus 400 miles per hour. All right, so the plane is flying fast in this direction, and when the distance from the radar station to the plane is 10 miles, this distance is decreasing at a rate of minus 400 miles per hour. And the question is, find the speed of the plane. Right? The plane's not flying at 400 miles an hour. This distance is decreasing at a rate of 400 miles an hour. The plane is flying at some constant speed. So we have to figure out how to solve this problem. So suppose we let x be the horizontal distance from the plane to the tracking station. So this is x, which means this is also x. That's the same thing. And that's a right triangle. So what we have is that this is 6, this is x, this is s. And we want to find the speed of the plane, dx dt. So we ask for a relation between what we know, s, and what we want to find out, which is x. And a simple relation is just the Pythagorean theorem. X squared plus 6 squared equals s squared for a right triangle. Right? Sum of the squares of the sides is the square of the hypotenuse. So if you differentiate with respect to t, both sides of this equation, the derivative of x squared with respect to t is 2x dx dt. Derivative of a constant is 0. The derivative of s squared is 2s ds dt. So what this says is that dx dt is equal to 2s ds dt divided by 2x, and the 2's cancel.
Professor, can you move the paper? Thank you.
Okay. ds dt is minus 400. Minus 400 s over x. What are s and x at the time we're interested in? When s is equal to 10, this is a 3, 4, 5 right triangle, x has to be equal to 8. So when s is 10 and x is 8, you get minus 400, 10 over 8. 8 into 400 is 50. This is minus 500 miles an hour is the speed at which the plane is flying. So let me go over this problem again, because there's a lot that goes into it. There's a radar station on the ground. There's a plane flying at an altitude of 6 miles above the ground in a straight line on a flight path that's going to take it directly over the radar station. And the radar station can measure the distance from the radar station to the plane. And it can also measure how fast this length s is changing. And at the instant of time, when the plane is 10 miles in a straight line to the radar station, when s equals 10, ds dt is changing at a rate of minus 400 miles an hour. It's decreasing because it's moving in this negative direction. And you want to deduce from that how fast the plane is actually flying. So, of course, if the plane is 6 miles high and it's 10 miles to the radar station, the distance, the horizontal distance, the number of miles the plane is from being directly over the radar station, you just solve this right triangle for x. If this is 6 and this is 10, this is 8. It's like a 3, 4, 5 triangle multiplied by 2, 6, 8, 10. So at that instant of time, this x distance is equal to 8. And from the Pythagorean theorem, x squared plus 36 equals s squared. If you differentiate, you get this relationship, this relation between dx dt and ds dt, and you plug in the values which we know for s and x and ds dt, and you get the speed of the airplane is 500 miles an hour. Okay. I'll do one more problem, and then we'll continue on Monday. So this is example 5, angle of elevation. So here you are on the ground, and 2,000 feet away, a rocket is being blasted up into the air. And you look at the rocket and say you're looking at it with a telescope, and it's going up. And as it goes up, this angle theta is increasing. So this angle theta is called the angle of elevation. So we're told, we're given, oh, and S is the distance from the observer with the telescope to the rocket. And this thing is shooting up in the air. And we're told that ds dt, this distance is changing at a rate of 100 t. Sorry. The height of the height of the rocket is s. That's what we're doing. So the rocket is shooting up into space. At time t, its height s above the ground, and it's going faster and faster and faster. The SDT is 100 feet per second. And the problem is to find the rate of change of the angle of elevation, d theta dt, when t is equal to 10. So here you are watching the rocket with your telescope. At time 0, the rocket, which is 2,000 feet away, is being shot up into space. And its velocity, ds dt, is 100 t feet per second. It's going faster and faster and faster. And as it goes up, the angle of elevation is increasing. And you want to find d theta dt when t is equal to 10 seconds. So what we need is a relationship between, so must find relation between s and theta. We know ds dt, we want to find d theta dt. And the simplest relation is the following. If you look at this right triangle, the tangent of theta, opposite over adjacent, is s over 2,000. So the derivative with respect to time of the tangent of theta with respect to theta, of tangent of theta, this is the derivative of tangent theta d theta times d theta dt. And this is equal to derivative of the tangent is secant squared theta d theta dt. But the tangent is s over 2,000. So that's the same as the derivative of s over 2,000 dt, which is 1 over 2,000 ds dt. So we have this relationship. 1 over 2,000 ds dt equals secant squared theta d theta dt. ds dt is equal to 100. So d theta dt, if you solve, just bring 1 over secant squared theta, 100 over 2,000. This is 100 over 2,000. 1 over the secant is cosine squared over 20. What is the cosine of theta? Well, if this is 2,000 and this is s, this is the square root of s squared plus 2,000 squared. So this is 1 over 20. Cosine squared is 2,000 over square root of s squared plus 2,000 squared, all squared. Let me just review what we've done so far, and then I'll finish the problem. So here you are 2,000 feet away from a rocket launch site. The rocket is shot up into the air, and its height above the ground, s, is increasing at a rate of 100 t. So t seconds from liftoff, the speed of the rocket is 100 t feet per second. You're following it with your telescope. The angle of elevation is theta. You want to find d theta dt at the time t equal to 10 seconds. So you need a relationship between theta and s. And one relation is that in this right triangle, the tangent of theta opposite over adjacent is s over 2,000. So if you differentiate with respect to time, the derivative of the tangent of theta with respect to t is secant squared theta d theta dt. Which is the derivative of this with respect to t, 1 over 2,000 ds dt. ds dt is 100 t. So we have secant squared theta d theta dt is equal to this. So d theta dt is 1 over secant squared 100t ds dt over 2000. Secant squared is 1 over the cosine, so 1 over the secant is cosine squared times t. Oops, did I do that wrong? Oops. Yeah. So 100t, when t is equal to 10, this is 1,000 over 2,000, which is just over 2.
Professor, how'd you get 1 over secant square?
I divided. I have secant squared theta d theta dt. So divide by, so that's equal to 1 over secant squared times this.
All right, thank you.
I'm just dividing by this. So d theta dt is 1 over secant squared times 1 over 2000 ds dt. ds dt is 100t. And I want, and 1 over secant is cosine. So this is cosine squared. ds dt is 100t. Let me write it down on a clean piece of paper. So this is 2000, this is S, this is my angle theta. We're told that ds dt is 100t. And the relationship between S and theta is tangent of theta is S over 2000. And if this is a right triangle by the Pythagorean theorem, this is the square root of S squared plus 2000 squared. So from this relationship, the derivative with respect to t of tangent of theta is secant squared theta d theta dt. Or if you like, I can write this as 1 over cosine squared theta d theta dt. And this is equal to the derivative with respect to time of S over 2000, which is 1 over 2000 ds dt. And we're told ds dt is 100t. 100t over 2000, which is t over 20. So these are equal. So d theta dt is equal to cosine squared theta times t over 20. And so we want to find d theta dt when t is equal to 10 seconds after launch. So when t equals 10, this is 10 over 20 cosine squared theta. That's a half. What is the cosine of theta? This over this. 2000 over the square root of S squared plus 2000 squared, all squared. So this is 1/2 2000 squared over S squared plus 2000 squared. what is S? So if ds dt is 100t, then S is equal to so what function, when you differentiate, gives you 100t? It is 50t squared. And so S, when t is equal to 10, is 50 times 10 squared, is 50 times 100, is 5,000. So what we get is this is 1/2 2,000 squared over 5,000 squared plus 2,000 squared. This is the same as 1/2. See, this is 2 million over 25 million plus 4 million, 2 million over 29 million, sorry, 4 million over 29 million, 4 over 29, which is 1/2, 2 over 29. So that's the answer. d theta dt is changing at a rate of 2 over 29 radians per second. Okay. Excellent. Well, what I encourage you to do is spend as much time as possible this weekend studying implicit differentiation, which is used in every related rate problem, and working on related rate problems. And I'll spend most of Monday going over some of these problems again and homework problems as well. But this is a very important topic in calculus. It's one reason why you study calculus, because you can solve applied type problems like this. Any questions about any of this for today? No? Okay. All right. Well, have a good weekend. Stay healthy, work hard. Be back on Monday. Bye, everybody.